Okay, any questions? Any questions? Yes, Mariah.
Can you go over using epsilon delta for sequences?
For sequences, okay, yeah. Like, so, sequences is, let me just do a very simple one. So to show that the limit of 1 over n as n goes to infinity is 0. Okay, so, so again, what that means is that given a range around 0, given a tolerance around 0, right here is 0. Given a tolerance around 0, there's a time past which everybody satisfies that tolerance, right? So given epsilon greater than 0, there's a time so that whenever you're past that time, n minus 0, 1 over n minus 0 is less than that tolerance.
Can you say that again?
Yeah. So I'll write it in English. Given a tolerance epsilon, there is a point, and past which all a sub n are within epsilon minus 0. Right. So these are the a sub n's, right? And we're saying that the a sub n's are within epsilon of 0. Right. So for example, right. So here's a simple one. If somebody says, I'd like, I'm going to take an epsilon of a third, say. I'm going to take an epsilon of a third. Can you find me a time past which? Can you find me a point past which all of your elements are within a third of 0? And you'd say, yeah, sure. If I take, for example, time 4, right? Then past that time, at time 6, 5, 6, 7, 8, blah, 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 you see what my points are. They're 1 over 5, 1 over 6, 1 over 7, right? And all of these guys are within a third of 0, right? All of these guys are within a third of 0. If I said, I'd like you to stay within a tenth of 0, well then, what would you choose as your time? 11, or 10, even 10 would work, right? Because at 10 itself, the guy is at, the height is 1/10, and anything past that is going to be less than 1/10, right? So this is a very, very simple example. And you just find a time and say, well, and if somebody gave you a height of epsilon, then what would you say? Just by analogy, if when my height was 1/10, right, I needed time 10. When my height was 1/2, I needed time 2. When my height is epsilon, I'm going to need time 1 over epsilon, right? So just take epsilon. Take n to be any number greater than any whole number. Greater than 1 over epsilon. In fact, we could use that funny notation that we had before in one of your homework problems, right? The smallest integer bigger than 1 over epsilon, right? That would be the next one. Yeah, Claire.
How do you do that algebraically, though?
How do you do it algebraically? Well, you'd say, well, you do some scratch work. You'd say, well, I want n so that if n is bigger than n, 1 over n minus 0 in absolute value is less than epsilon. So you start thinking about it, right? You start thinking about it, and you say, well, I know this 1 over n minus 0 is a positive number, so I can pull off the absolute value signs, right? Further, subtracting 0 doesn't do anything, so I can do something like this.
Wait, how did you know 1 over n minus 0 is a positive number?
Because 1 over n, these are all, n starts from 1,
Okay.
right? These are not negative.
So you can't-
You don't start your sequence from negative numbers, typically. You could, but typically one doesn't. You start your counting from 1, 2, 3, 4, 5.
What does the capital N represent?
The time, the time past which everybody, you're looking for that n, you're looking for the time past which everybody satisfies the tolerance. It's this thing here.
X, basically, the x coordinate.
Yeah, you could think of it as an x, right? If you're thinking of this as an x. Right. But typically with sequences, you don't use x. With functions, you use x, and with sequences, you use like n's and capital N's.
Cool.
Just convention.
Okay.
Okay, so coming back here, you're looking for the time past which this happens, right? So you want n so that n bigger than capital N implies 1 over n is less than epsilon, right? This is how you're thinking, right? Well, what n will do? For 1 over n to be less than epsilon, right? For 1 over n to be less than epsilon is the same thing as saying that 1 over epsilon is less than n. Right? You can multiply both sides by n, which is positive. You don't change the direction, right? You divide both sides by epsilon, which is positive, right? So the question is, what capital N will ensure that that little n is bigger than 1 over epsilon? Well, just take your n to be 1 over epsilon. Right? So take n to be bigger than 1 over epsilon. Right? Because then if n is bigger than that, if little n is bigger than that, that means that little n is that 1 over little n is smaller than 1 over epsilon. Right? Yeah, Stefan.
No, never mind. I figured it out. Thank you.
Right? So you do some scratch work, and then you think, okay, and then you write it down. You say, just take n to be bigger than 1 over epsilon for if this is how you write it up. For if n is bigger than capital N, which is bigger than 1 over epsilon, then 1 over n is less than 1 over capital N, which is less than epsilon, right? Which is what you wanted. You wanted a time so that if we're past that time, then 1 over n is smaller than epsilon, and you found it. Right? Just take capital N to be bigger than 1 over epsilon, for then if little n is bigger than that, then 1 over little n is smaller than epsilon. Anyway, that's how you do it algebraically. But in this case, it's more straightforward. You just look at it and say, oh look, it's decreasing. You can do it more intuitively. I mean, yeah. Does that help? I don't know. Does that help? I don't know. I hope it helps. In any case, what's the game, right? The game is to show that given an epsilon, there's a time past which all your sequence elements are within epsilon of the limit, right? What does this mean? To show something like this, it means that you have to show that given any here's L, given any epsilon, there's a time, given any epsilon, there's a time past which all your sequence elements lie that close to L. Okay.
If the limit is infinity, it'd be like there's like past which like it'll be closer to infinity.
So that's something that's a little bit different, right? For the limit to be infinity, to show that the limit of a sequence is infinity means that given any bar, there's a time past which all elements are past that bar. Yeah, right. So, if we say show that the limit of x as x goes to infinity, the limit of n as n goes to infinity is infinity, well, you would say, if somebody gives me a bar of m, then where should I be? Where do I need to, what should be my time over here?
You can be anywhere, like
Anywhere?
well,
But-
like it not it like it ends. Oh, sorry, no, never mind.
Okay, right. How far out do I need to go to ensure that all of my elements are past the bar, or over the bar? Here are my elements, right? At time 1, I'm 1. At time 2, I'm 2. At time 3, I'm 3. How far out do I need to be? M, right? Right? As long as I'm past M, then everybody's above the bar. Right? Okay, and that works for any M, right? If somebody gives you a million, you say, past time a million, everybody's above your bar. Somebody gives you a billion, say past time billion, everybody's above your bar. Right? And that works for any M. And so you see that the limit actually is infinity. Yes, Sarah?
Wouldn't n be on the bar? Like, does that kind of like for that?
Yeah, so you'd have to say past M.
Okay,
Yeah.
okay.
So you need to say, and that's part of it. You usually say, given any M, there exists time so that past that time, then everybody's above the bar. Right. Past that time, everybody exceeds that bar. Whenever you pass that time, everybody exceeds the bar. So yeah, but you're right to be careful about that. Okay. I see you're all thinking about the exam.
Yeah.
That's good. That's good. Okay. Okay. So let's get on with the material. So what can we do right now? So we're talking about differentiation, right? So today we're going to talk about sort of like expanding the repertoire. So what can we do right now? What can you differentiate in this way? What can you differentiate right now? Claire, yes?
Any polynomial with degrees that are natural numbers?
Yeah, any polynomial. So generally, when one says polynomial, the degrees are definitely going to be natural numbers. Okay, so any polynomial. What else? Is that it? Just polynomials? You can do one more thing, maybe. Yes?
Sine and cosine.
Sine and cosine. Yeah, we mentioned them at least. We know how to differentiate sine and cosine. And what else?
Tangent?
Can we do tangent? No, we can't. Not yet. But we could do some, just to be sort of dumb about it, we could do like 5 sine. We could do sine plus cosine. We could do sine plus any polynomial. We could do 5 sine plus any polynomial. We can do, so we can do things like this, and what are called linear combinations of these functions. and when we say linear combinations, we mean combinations involving addition or multiplying by a number, by a scalar. That's to say a number. Okay. Right. So any sort of combinations, right, we could take, 5 sine x plus 2 cosine x plus some polynomial, right? And that we can differentiate this sort of thing. Okay. And that's about our limit at this point. Right. Yeah.
Just to
Question.
clarify, differentiating is just being able to find the derivative.
Yeah. Differentiating just means what can you take the derivative of?
Okay.
So. What can you find the derivative of? Yeah. Okay. So that's about all we can do. Can we do something like this? Can we differentiate something like this? At this point, no, right? Although we could do it, we can do basically anything by hand, right? So we could try this by hand. We could say, sure, we can. Let's take the limit of sine x plus h cosine x plus h minus sine x cosine x, everything over h as h goes to 0, and then start applying trigonometric formulas, wildly, right? We could, and we would find the right answer. Yeah.
Wait, isn't that just like two functions multiplied together? Then?
Yeah. So this is a multiplication, a product of functions, which
And
it's not a linear combination.
Okay.
Yeah, we can multiply by a number,
Yeah.
right? We can do 5 cosine x, but we can't do sine x cosine x.
Okay.
Okay. So that be clear that this is not a linear combination, not multiplying by a scalar, but multiplying by another function. Okay. So so we could do it directly, but luckily for us, fortunately. There's a general formula. So called the product rule. So remember last time we said that the derivative of a sum is going to be the sum of the derivatives, the derivative of a multiple is going to be the multiple of the derivative. Now we have something of the derivative of a product. And what would you hope it would be? The derivative of a product is the product of the derivatives, but that's actually not true. Okay. So people are shaking their heads, it's not true. Rather, the derivative of a product is going to be, does somebody know it? Emma, you shook your head, so maybe you know it?
Well, I remember it's like f prime
Yes.
times g of x
Uh-huh.
plus g prime times f.
Uh-huh. Yeah. So f prime g plus f g prime, or f prime g plus g prime f, however you want to write it. Okay. So for example, this function that we're talking about here, if we're differentiating sine times cosine, right, then that's going to be the first guy's derivative, which is the cosine, times the second guy, plus the first guy times the derivative of the second guy. And what we said last time, although we didn't show it, was that the derivative of cosine is negative sine. Okay, so you get cosine squared minus sine squared. Okay, so to write it more formally, if f and g are differentiable at c, then f times g is also. And the derivative of the product at c will just be fill it out. Okay, so being two functions being differentiable at a point means that their product will be differentiable at that point.
This is possible if we want to be differentiable and one not to be.
Then all bets are off. Yeah.
Okay.
So who knows what happens then? Yeah, in that case, this rule doesn't apply. Okay, so that's a product rule. It's easy to excuse me, easy to use. Sorry. Why is it true? Let's think about the limit of f times g of c plus h minus f times g of c over h as h goes to 0. Right. What we're saying is that that's going to actually end up being f prime c g c plus f of c g prime of c. Right. We're saying that that's going to be the limit for for f times g of c plus f of c times the limit for g. Right. Okay. Maybe that's not completely obvious that these two things are the same thing. This is that. Let's see how we get from from here to there. Okay. So, sorry, maybe I should take a cough drop. Okay. So let's just write it out. F of c plus h, g of c plus h, minus f of c, g of c, everything over h. H goes to 0. Okay. Now, do you see, we're sort of hoping to see something like f of c plus h minus f of c over h in here. Right? That's what we're hoping to see. But you don't see it. Do you see it? You sort of see it, maybe. Anyway, it's not really in there. Okay. Do you see that? Does anyone see this thing in here? We can't really factor such a thing out, right? Because we're gonna do something funny, which is we're gonna put it in there. Okay. We don't see it. We would like it to be in there. We're just gonna put it in there. F of c plus h, g of c plus h, minus f of c, g of c plus h. Everything over h. You're going to say, how can you just do that? You can't just put in f of right? So you see what I'm doing, right? I'm sneaking in the thing that I want, right? But I can't just throw that in whenever I feel like it. So I'm going to take it out also. So I'm adding in a funny 0. I'm adding in cleverly chosen 0. Right? This thing in the middle, I'm subtracting something, I'm adding on something. So some of you are looking sort of like befuddled? No. Befuddled. Okay, yes. People are nodding at this word, befuddled. Okay. Yeah. So why did we do that? Because we're hoping to have this f prime c in there somewhere, right? So we just sneaked it in, right? We just sneaked it in. Right? If I factor g of c plus h out of this first thing, I get g of c plus h times f of c plus h minus f of c over h. Right? That's this first part right here. Right? And then, what do I have? The rest of it is, looks like I have an f of c, and then I have a g of c plus h minus g of c over h. All I'm doing is splitting this thing up into two parts, right? And using my knowledge of fractions. Right? I split it into two parts. Out of the first one, I factor out of g of c plus h. Here it is. What am I left with? F of c plus h minus f of c over h. In the second one, I have f of c times this minus f of c times that. So I factor out the f of c, and what am I left with? G of c plus h minus g of c over h. Okay, everyone okay with that? That's just elementary school, right? Fractions. Okay, but now you see it starts to look good. It starts to look pretty good, right? As h goes to 0, what happens to this thing? G of c plus h minus g of c over h. G of c plus h minus g of c over h. This is as h goes to 0. G prime, thank you, Nora.
Oh, right.
G prime, right? What happens to this thing? It is f prime. And what happens to this thing?
G of C.
G of c. G of c, because g is continuous at c. Right? The limit as h goes to 0 is going to become g at c itself. So we actually use the continuity of g here. Right? Okay. And there you have it, right? You get f prime times g plus g prime times f. So the product rule, it's true. Right? The derivative of a product is not the product of the derivatives, but the sum of the derivative of the first guy times the second plus the first guy times the derivative of the second. Okay. Right? And so that's why we can do this sort of thing. Okay. Suppose I gave you something like this, x squared sine x cosine x, and I asked you to differentiate that. So you have three things now. Think about it for 15 seconds and then tell me how you would do it. You don't have to do it, but tell me sort of the strategy of how you would do it. Okay, how would you do it? Anybody? Stefan.
Would it be like saying like 1 f, 1 g, 1 h, like f prime g h plus f g prime h plus f g h prime?
So let's think. Or let me think. Right. If you have three functions and you're taking the derivative of them, well, the product rule says that you can take the first guy times the derivative of the second guy, say, plus the first guy's derivative times the second guy.
Oh.
Right? And so you can sort of, there are three functions involved, but you can think of them as two.
Yeah.
Right? So the strategy is pretend that there are only two functions, and you choose your two functions however you like. You could say, this is my first function, and this is my second function. Or you could say, this is my first function, and this is my second function. Or you could say, this is my first function, and this is my second function. I don't know, however you like. Okay. So, so I'm going to do it this way that I indicated first. Right. So you say, okay, I'm going to get then the derivative of the first function times the second function. Right? The derivative of the first function times the second function plus the first function times the derivative of the second function.
How do you know x squared?
Because the derivative of x squared is 2x by the power rule.
Oh, yeah.
You remember that?
Okay.
Yeah. So 3dx of x squared, the derivative of the first guy times the second guy, plus the first guy times the derivative of the second guy. Right. And then by the power rule, you know it's 2x. Right. And then you come to here, and you use the power rule again. Use the product rule again. Right? So you say, okay, this is going to be the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy. Right? And so altogether, you end up with 2x times cosine x plus x squared cosine squared x minus sine squared x. Yeah, all right.
So is x squared not a scalar?
Not a scalar, it's a function.
Yeah. Oh, yeah, because
Yeah.
x isn't constant.
Because x is changing,
Yeah.
right? Yeah, so it's not constant,
Mhm.
right? It doesn't have x squared depends on what x is.
Yeah.
Yeah, it's a function. Yeah, so you have to distinguish between scalars. It's really important to distinguish between a scalar and a function, right? You can't say, oh, this is a scalar. I mean, sometimes people will think, this is just some number. So can't I just pull that number out? But this is a number that's changing, right? Changing wherever you evaluate it. So it's not just some number. Or you might think like this, these are all just numbers, right? So this thing is a constant, and when I differentiate a constant, you get 0. Right? Okay, don't think like that. Don't think like that. Okay, this is not a constant, right? It changes as x changes, right? And we're asking, what's the rate of change, right? This thing changes as x changes. Now, if it's something that doesn't change with x, then it is a constant. So, for example, if I had some other thing here, x ddx yx squared, y is something, right? And and you know that y doesn't depend on x. Well, then that is a constant, right? And you just get y times the derivative of 2x. Okay. Yeah. Okay, because you're asking, the thing has to be constant with respect to the thing that's changing. Yeah. So you keep this dx in mind. Yeah, I remember thinking, that thing that you just laughed at is exactly what I thought at one point. Oh, the whole thing is a constant, so when you differentiate, you just get 0. No, that's wrong. It's not constant with respect to x. Okay. 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 There's another, the product rule. You also have something called the quotient rule. Okay. And again, it's not what you would like. Maybe you think that the derivative of a quotient is the quotient of the derivatives, but it's not true. Rather, if f and g are differentiable, let's see, then and g of c is non-zero, then the derivative, the quotient is differentiable at c, with the derivative of the quotient being, does anyone know this? I don't know.
Is it f prime g minus f g prime over g squared?
F prime g minus what?
F g prime.
F g prime
G squared.
bottom times the derivative of the top minus the top. Yes, that's right. Yeah. So yeah, the whole thing evaluated at C. So maybe I'll just yeah. Okay. So the derivative of the quotient is going to be the bottom times the derivative of the top minus times the derivative of the bottom over the bottom squared. Okay. And I think there's some song that people remember, like Lodi, highly low, something or other. Anyway, I don't. that clearly came out after I went through high school. So. Anyway, the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So for example, right, the tangent function, sine over cosine. Right? So take a minute and do it using the quotient rule. Okay, so what do you get? Well, you get the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Right? And you see what happens, so you get cosine squared plus sine squared. Well, what's that? 1. And so you get 1 over cosine squared. Let's just say the secant squared. So the derivative of the tangent is secant squared.
How'd you get to that 1?
Cosine squared plus sine squared. Right? Cosine. So this top thing here is cosine squared plus sine squared over.
Okay.
Right? And what's cosine squared plus sine squared? Well, remember what cosine and sine are. They're coordinates on the unit circle. Right. Right. So being on the unit circle means that this x squared plus y squared is going to be 1. Okay. Clear how to use this? Yes, fun.
Would it also be true to once you have cosine squared x plus sine squared x over cosine squared x, then cosine squared x over cosine squared x plus sine squared x over cosine squared x, you get 1 plus tangent squared x?
Yes, that's true.
And that also equals secant squared x.
Yes, right. 1 plus tangent squared equals secant squared.
Okay.
Right. Same thing. Yep. Right. Yeah, so you could certainly write this as 1 plus sine squared x over cosine squared x. Right. Which is 1 plus tangent squared x. Okay. Any questions about that? Pretty. Again, it's just a matter of remembering it. We could show you how this one works as well, but it's a bit more involved than the multiplication one, so we're going to skip it. It's not hard, but you've already seen the multiplication one, and it's sort of the same idea. You make it look as you would like it to make it look. Okay. So that's pretty useful, right? Now at this point, you can differentiate certain functions, right? You can differentiate these functions, right? You can differentiate any linear combinations of those functions. You can differentiate any products or quotients of the above, right? And you can take products and quotients and linear combinations of products and quotients, right? So basically, not just of the above, but of themselves as well, right? So any products and quotients. Right? So now your repertoire has increased considerably, right? Thanks to these two rules. Okay. In the next section, we'll see two things. One, that the power rule holds for all real exponents. Right, that is, if you're differentiating x to the r for any r, okay, for any real number r, you know, the derivative of x to the r is going to be r x to the r minus 1. Okay. And we'll see another thing, that if you differentiate the exponential function, then you get, does anyone know? You get the exponential function back. So these will sort of enrich the rules here, right? You can now throw in the exponential function into this mix and do more things. Okay, but I think maybe we'll just stop here for today.